Hello and welcome to today's webinar from Gen-Z Consortium. We will begin the webinar in about 2 minutes so that we can allow for other participants to join. If you do have questions during the webinar, we will be answering those at the end of the presentation. Please use the question tab to submit those. Thank you. Hello everyone and welcome to the third in Gen-Z's ecosystem series of webinars. Today's webinar, Real World Applications of PECFF for Increased Performance and Disaggregation. It will be presented by Steve Krooswyk, Ralph Page, and Matt Burns from Samtec, Inc. If you do have questions during the webinar, please use the questions tab, and all questions will be answered at the end of the presentation during our live Q&A session. Enjoy the webinar.
Thanks, Rachel. This is Matt Burns, Technical Marketing Manager here at Samtec. As Rachel mentioned, joining me is Steve Krooswyk and Ralph Page. Before we get started, maybe we could ask Steve and Ralph just to give a brief intro.
Hey, this is Steve Krooswyk, SI Engineering at Samtec, and I'll look forward to sharing more content with you later in this talk.
And Ralph Page, Systems Architect with Samtec. I'm going to show you a demo that we put together for this a little later on. Thank you.
Thanks, Steve. Thanks, Ralph. We'll look forward to your part of the presentation in just a few minutes. So here's a brief overview of our agenda for our webinar today. One of the things that we're going to look at are some of the high-level data center trends that Samtec sees from our perspective as a supplier to data center equipment manufacturers. We'll talk about the benefits of the Gen-Z Scalable Connector as defined by SFF TA 1002. What is PECFF? Obviously, that's a key part of our webinar, so we'll define that and review some of the high points of the standard. The real focus of our presentation today is to talk about a real-world PECFF emulation platform that Samtec has developed, and then to look at the performance that this emulation platform offers for those that are interested in designing PECFF platforms. In those two sections, we'll rely on the expertise of Steve and Ralph to help us show what's possible from a performance standpoint with PECFF platforms or solutions. We'll have a brief summary, and then as Rachel mentioned, we'll finish up with Q&A at the end of the webinar. When we look into data center, at least again from Samtec's perspective as a component supplier to data center equipment manufacturers, one of the things that we're seeing is the ever-increasing need for speed. Right now, current generation products available for data center equipment typically feature 56 GPM4 channel data rates. Silicon solutions at those data rates are commercially available as we speak. But in recent months, we've started to see several leading semiconductor companies start to announce their roadmap products for 112G PAM4 solutions. This is just a snapshot of some of the tech that's been released in recent months. Innovium recently released their TerraLynx 8 high-performance switch targeting networking applications within the data center. Within a single 1U box, you can get 25.6 terabit per second throughput using 112G PAM4 SerDes. In a similar vein, we see that Xilinx continues to expand their Versal family of ACAPs. They recently released their Versal Premium series, which is one of the first solutions, if not the first solution, that they offer that supports 112G PAM4 transceivers within the silicon. And then towards the front panel, we see that Inphi has come up with the world's first 800 gigabit per second PAM4 front panel solutions. So when you look at these press releases compositely or holistically, you see that 112G PAM4 solutions for data center switches, front panel electro-optics, and for FPGA-based or ACAP-based acceleration platforms have been announced, and silicon will be available within the early part of 21. So in general. So this helps us to see that 112 gigabit per second performance is real, and that the performance of data center solutions continues to increase. Another trend that we're seeing within the data center is disaggregation. Obviously, Samtec is not an IT equipment vendor, but from our perspective, we kind of see disaggregation as the ultimate in open source data center design. Why do we say that? Well, instead of purchasing your chipset or your white box hardware and your network operating system all integrated into a single solution, disaggregation allows you to piece those solutions together to come up with a platform that is ideally suited to your data center utilization and data center demands. This optimizes performance within the data center and helps to improve management of power and cooling within the ecosystem. So when we look at both of these trends at a very high level, both increased performance to 112G PAM4 and also disaggregation within the data center, Gen-Z, the flexibility of the fabric and the performance of the protocol really ties into these trends. So what we're going to look at going forward is how the Gen-Z consortium is responding to these trends. The first section that we're going to look at is the Gen-Z Scalable Connectors, originally defined by the Gen-Z consortium and now a part of SNIA. These do provide a pathway to 112G PAM4 performance. So just a brief overview of Gen-Z Scalable Connectors. As we mentioned earlier, these are defined by what is now the SNIA SFFTA 1002 specification, which covers mechanical and electrical details of the connector. The actual pinouts are defined by the various form factors that use the connector. We'll talk about that in just a moment. Gen-Z Scalable Connectors are available in 4 variants, 1C, 2C, 4C, and 4C+. These have been specifically designed to be mechanically interoperable. So a small connector fits into a large connector, and a large fits into a small. The options available in terms of sorry, I lost my word for a second. In terms of options available, there's vertical, there's right angle, there's orthogonal, straddle mount, and cable solutions for the Gen-Z Scalable Connectors. These do support multiple physical layers, PCI Express, Ethernet electrical, Gen-Z. One of the benefits of the Gen-Z Scalable Connector is the fact that it has a very high density pitch. The pins are spaced 0.6 millimeters apart. We'll talk about, when we get into the performance of the connector, some of the benefits that provides. Steve will provide some details on that. But at a high level, that allows us to optimize SI, an effect-free, low latency ecosystem. And the fact that we use the same connector enables multiple connectors per module, again, increasing density and increasing performance. One of the beauties of the Gen-Z Scalable Connector, defined by SFFTA 1002, is the fact that it has been adopted by a number of form factors, EDSFF, NVMe drives, OCP NIC 3.0, PECFF, SFFT TA1021, which is what we'll talk about, and high-speed cable solutions all use this same connector. So that drives volume, streamlines sourcing, and makes the solutions cost-effective for a number of applications. Some of the benefits that we see with the Gen-Z Scalable Connector is the application flexibility that's illustrated here. We can see that Gen-Z Scalable Connectors can be used for internal add-in cards, which we'll obviously talk about within PECFF, hot pluggable modules, electrical cables, and there's also optical transceiver options as well. The solutions are forward and backwards interoperable, so that does provide a migration path to higher speed performance as protocols continue to evolve. Another benefit is that the connector itself is protocol agnostic. So as we mentioned previously, a common connector can be used in multiple applications such as storage, PCI, or memory, which again allows for increased volumes of the connector to be manufactured across multiple suppliers, simplifies supply chains, and reduces costs for the end user. Next, we're going to turn it over to Steve, and he's going to talk about some of the performance benefits of the 0.6 millimeter pitch Gen-Z Scalable Connector. Steve?
Sure. Thanks, Matt. I'll be happy to point out a couple things. Two charts for you. This one is the differential insertion loss of the Gen-Z Scalable Connector, and this, what it does is it demonstrates the ability to pass a high-speed signal successfully through the connector. The purpose of this chart is really to contrast Gen-Z to maybe the typical industry standard. The Gen-Z Scalable Connector is the small pitch connector, the green curve on 0.6 millimeter pitch, showing an excellent loss performance to very high frequencies, really demonstrates a pathway out to 112 gig PAM4. And then that's contrasted to the red curve, which is like a traditional edge card style on a 1 millimeter pitch. And one can observe the difference in the bandwidth capability between the Gen-Z solution and the prior traditional solution. So it's a stark performance difference in capability. The second chart I have for you, flipping the page, is kind of goes along with that and the same message. It's the return loss for the connector. So it's how much noise is returned from the Gen-Z connector. And lower is better. And the Gen-Z Scalable Connector shown in green, showing a much, really across the entire frequency spectrum, a much lower noise return than the red traditional 1 millimeter style form factor. Okay, so all around better at passing the signal through and reducing the amount of noise that comes back. Thanks, Matt.
Thanks, Steve. So next, we'll actually start to define what is PECFF. Very simply, the acronym stands for PCI Express Enclosure Compatible Form Factor. But what are some of the benefits of that infrastructure? One of the first and foremost benefits of PECFF is it is mechanically compatible with PCI Express CEM add-in cards. PECFF also supports the 4 PCI Express CEM AIC sizes, half, 3/4, full, double width. As we mentioned earlier, it does comply with the SFFTA 1002 mating interface, so supports 1C, 2C, and 4C connectors, which provides a pathway for performance of up to 32 gigatransfers per second with PCI Express Gen 5. As well as supporting other interfaces such as, or other protocols such as IEEE 802.3 electrical with a pathway of up to 112 gigatransfers per second PAM4 data rates. One of the things that we see in the performance specs that Steve just showed is the confidence that PECFF users can have leveraging the performance of the SFFTA 1002 interconnect. PECFF also supports an optional second connector, which allows for an increased density of signaling throughout the AIC. whether that's a single by 32 symmetric link of PCI Express or multiple link options for Gen-Z. PECFF also supports 48 volts, so that provides power efficiencies at the system level versus a 12-volt infrastructure, which can provide OPEX savings for data center providers that use PECFF as well. Moving on to the next slide, we see some other fundamentals of PECFF. We talked earlier about the benefits of disaggregation. In essence, providing an open source model for data centers. PECFF has been designed to support just that. Any one AIC or one component can support any number of functionalities: flash, SCM, DRAM, GPU, GPGPU, FPGAs, DSPs, ASICs, whatever the case may be. It does also support multiple interconnect technologies, PCI Express, Gen-Z, among others. Another benefit of PECFF is the fact that it supports add-in card top edge connectivity. That's one of the things that Steve will talk about when he gets into the performance section of the emulation platform that Samtec has developed. One of the other benefits or fundamentals of PECFF, it does support active or passive cooling solutions, and it has shifted the card edge 60 millimeters closer to the processor. This provides some SI benefits, recovering up to 8 dB of loss on the motherboard, and we also see improved performance on the AIC because the trace lengths are shortened and device layout is optimized. These SI improvements minimize the need for retimers and high-cost, low-loss board materials within the AIC and also within the motherboard. We talked earlier about one of the key benefits is top-edge connectivity. This slide really helps us to see the benefits that this essential part of PECFF provides. Additional connectivity through the top of the card, being able to route up to 128 differential signals plus reserve pins from one card to another, or from one AIC to the motherboard that it plugs into. The top edge connectivity uses the same mechanical pin and pitch as SFTA 1002, and it is able to support any physical layer or protocol. There are multiple connectivity options that are available. One of the benefits, again, of the flexibility of the PECFF standard is that a top edge connector or latching system is not provided. So that allows interconnect suppliers like Samtec to provide a variety of solutions that optimize performance or optimize application-specific solutions on a customer-by-customer basis. Another benefit of top-edge connectivity within PECFF is that it specifies the order to provision signal groups to help reduce cost and complexity within the system and to improve interoperability between add-in cards. This is another illustration that helps us to see the flexibility and benefits of PECFF within a data center. This really optimizes the whole concept of disaggregation. We can see that a PECFF chassis can support any mix of PECFF or PCIe CEM add-in cards. Some of these could be configured as memory, some of these could be configured as servers, some of these could be configured as graphics cards or acceleration platforms. Really, again, showing that PECFF is ideally suited for disaggregated infrastructure within a single chassis. This also leverages the flexibility and scalability of the Gen-Z fabric. At a high level, we talked about in the overall introduction of the webinar that PECFF really drives disaggregation across the data center. Some of the benefits that we see are that servers can be composed to optimize their resources to fit the specific application or load within a data center. We can unlock trap resources in the sense that if we're underutilizing an asset within the data center, disaggregation allows us to fully optimize it. We avoid over provisioning. We talked earlier about streamlining the supply chain and giving vendors the opportunity to purchase resources independently. We increase RAS. We also are able to repurpose retired resources, and because of the scalable nature and disaggregated capabilities within PECFF, that allows us to plug and play, and technologies can evolve and be deployed on an independent basis very easily. So so far we've summarized the Gen-Z Scalable Connector, the performance it provides. We've talked about PECFF from an overall standpoint, but we really want to focus on for the rest of our presentation is the emulation platform that Samtec has created, and look at the performance that's achievable by using this. So we're going to turn it back over to Steve and let him detail the work that him and his team has done.
Okay, thank you, Matt. So let's talk about the emulation platform, introduce it, and talk about the problem that it's trying to solve. The problem that we were thinking about solving here is the silicon and PHY designer or the OEM platform designer that wants to test the PECFF style interconnect and is looking for a way to do it, right? We know these add-in card and ganged add-in card form factors are gaining popularity, as Matt just cited. They're particular electrically in their number of connectors, their PCB lengths, and the amount of noise that they have that you face from a signal integrity point of view. And what we said was, you know, typically the simple length extender that a PHY developer might use in the lab is not realistic enough, meaning a single long trace doesn't include the reflections or the crosstalk style that a real system would experience, and one is interested in that to properly stress their equalization and do a proper lab validation and test a product. And then there's multiple topologies in the PECFF. We think about connectors, we think about cables. How can we evaluate those different types of stresses? And that's the need that the emulation platform seeks to fill. Shown here on the right in the photograph, the platform introduces a by two interconnect over multiple topologies. So there'll be one connector solutions, two connector backplane solutions going from card to card, and then top edge connectivity, or where you have the cable style backplane that goes from one card to another over the cable. To make this work, we use RF connections that have been optimized and impedance controlled. The platform, we want to have configurable losses for the cable and the PCB interface to test different scenarios. We design it for 85 ohms to match the connectors, and we entertain that the cable could be different impedances. We could interchange 85 ohm cable, interchange 100 ohm cable, and test for the performance and think about what's optimal. Maybe even something in between. A 92 ohm could be on the table too. So let's look at the connections within the chassis and the placements of the different items. So this is the rendering side view so that you can see the components a little bit better. The top edge cable connectivity being highlighted there. The Gen-Z Scalable Connector being found on the PCB backplane on the bottom. And then notice the multiple configurable positions along the backplane, 8 or 10 Gen-Z Scalable Connectors at different positions that would actually allow for different amounts of cable length or actually different amounts of test PCB length as well. On the next page, you can see where those connections are made. The cable interface with a short route to RF connectors highlighted in orange. Also highlighted in orange, card-to-card connections through the PCB backplane, passing through two connectors. And then highlighting also in orange what the one connector interface would look like through the backplane to one of the connectors and onto the plug-in card. So when we face the cable backplane or the cable interface, we start to think about the losses in the system, and we want to highlight that and talk about that as an important point here. So as we go to these higher speeds, the PCB loss is becoming increasingly important. It becomes larger and larger, and it steals more from our interconnect budget. The cable is an interesting solution to overcome the loss. We can traverse the same amount of length with a smaller amount of loss. I want to highlight the chart on the right demonstrating really the difference between a 10-inch path on a PCB in yellow, pink, and red, or a 10-inch path on cable with the very low signal loss in green and blue. So the value of cable loss is very apparent. The other item to highlight is the spread of the color. So the yellow is very a wide range, and the pink is a wide range, and this is representing the sensitivity to temperature and humidity on the loss. So that's the variation spread. So the cable has a very tight spread, or sort of a low response to temperature and humidity, while the PCB can have a very large and variable response. Okay, so that's actually an added benefit and added bonus of cable. Also, when we think about cable and making that connection across the backplane, you're thinking about the Gen-Z form factor or other form factors, we always have to think about having enough signals in that cable interface. So we think about our data signals, but don't forget about positions for reference clock, sidebands, other things as we're making our selections and testing different cables over that front end topology. So how do we pick our cable? How do we know that it's going to work in our Gen-Z system? Does it meet any specifications? How long can I make it? Those are all excellent questions. They're popular questions. The number one answer here is this is evaluated by simulation. Using the tools available to the industry, one can determine really what's the maximum length allowable for your cable and or PCB, or a combination of both. You know, simulation is a tool. Also, the emulation platform here is a tool. So we can empirically discover in the lab what's the combination of board and cable length that's going to work with my PHY and give me an acceptable bit error rate. With the cable attachment, there's multiple solutions out there, different ways to do this. One pathway is where the cable is soldered directly to the PCB, like in the upper graphic. Interesting, good, quick solution. The second option is where the PCB will solder directly to the connector. And so this is actually a little bit better. It bypasses the PCB interface and improves impedance and improves return loss. So that second choice is what we'll be reviewing today in the emulation platform. The direct attach is used on that platform. Okay, so features and the way that this platform might be used. In this illustration we're showing on the bottom, we would have a PHY evaluation board. We'd cable over to the test platform in the middle, and then we'd cable over to a PHY evaluation platform on the backside. Now the platform I mentioned has a by-2 interconnect for all its topologies, and what that means is there are 2 lanes for transmit and 2 lanes for receive. And what this will allow is a complete loop back from one PHY back to itself, or also maybe one PHY talking to another. So we can get that complete loop back, and we can also get the various crosstalk style from having more than one active lane available in the platform. We can get that realistic noise in our evaluation. The additional pairs, of course, are terminated to resistors that aren't being used, but every interface in this platform will have the 4 connectors, the 4 connections that you see connected on the slide. So on the next page, we start to think about let's determine inside the emulation platform what length of trace we need on the board for a proper and realistic evaluation. And the first place that we start to do this is what we like to call a first principles approach, where we think about what's the total amount of loss that we want to achieve and how much loss are our components going to use. We do this because it's really quick. We can do this in Excel. We believe it's 90% accurate, and it's much faster than spending a lot of time on simulation. It's expensive, takes time, takes resources, and maybe all the models aren't ready. So what we wanted to start with in the simulation platform was thinking about 32 gigatransfers capability. And so for 32 gig, we know that the target loss is 36 dB at Nyquist for all the packages, die, and interconnect. So we want to evaluate our emulation platform, make sure we get 36 dB. In this first principles approach, we don't think a whole lot about noise and reflection. We imagine that for these high-speed interconnects, that's managed pretty well. And we want to evaluate, at least getting to 36 dB. And we can test certainly solutions that are shorter than that, but we want to have the maximum capability for the standard available. So here's a couple examples. I'll just show you the three interconnect styles on the board. One was one connector interconnect, going from evaluation platform into the emulation chassis and then into another evaluation platform. And we assume that maybe about 6 dB of losses for the emulation platform on each end. And then we know the losses for our RF cables. And then we look for how much loss do I have left to get to 36 dB. And we increase the trace length of the emulation platform up to that mark so that we make sure that we get the full specification stress. The other thing we'd like to see is really a spectrum of losses available to different connectors on the board that we might test our silicon equalizers or other components when the channels are not at their maximums. And so we target about a 2 dB increment below the 36 dB mark to give us that spectrum of loss. So that was our approach. We did it for one connector design. We completed the same approach for two connector interface, passing through that backplane and choosing a couple of different lengths for the PCB backplane. And then we repeat the same thing for the cable topology, and determining what length we would think is appropriate on the riser card, and think about what different lengths of cable would also make sense. Okay, so same approach applied to all three topologies. So now that we've thought about what were the inputs into the design, we can start to look at some of the actual measured performance. So I'll show you what we measured on the platform. I will show you the results directly looking into the emulation platform. I'll include the RF cable, about 3 feet of RF cable on each side, but I won't include the evaluation platform. It would be independent on someone else's side that would be hooked up, okay? So just looking into the emulation platform, what do we see? And we'll see what we expect to see are the low-loss Nelco 85 ohm traces, the Gen-Z Scalable Connector, the cable, all of these items included in the interconnector we'll observe in the measurement. The first measurement I have for you is the differential TDR. So you see the first thing is coming in at 100 ohms is the RF cable. And then we see an immediate drop down towards the 85 ohm PCB, the Gen-Z connectors, and the cables as well. We see various different responses in time thanks to the incremental interconnects available in the chassis. So the shorter links show less time, the longer links show more time. And then this is exactly what we expect. There are different colors here. The blue represents the one connector topology. The red is the two connector backplane. And the light blue cyan color is the cable assembly with a few different cable lengths included. Maybe more interesting on the next page is the loss spectrum that you get. And this is really certainly what we'd like to see. If we zoom in on the chart and see where we are at about 16 gigahertz, we can see that we have quite a bit of spread in losses available to us for evaluation. We also see that the insertion loss is very smooth. There's not very much insertion loss deviation or noise as we pass the signal through it. This is really an indicator of the performance of the platform, the performance of the Gen-Z Scalable Connector, and the capabilities that you have when you pass through cable interconnects. So just a good attribute to those electrical characteristics. One more is the return loss metric that we measured on the platform for all three interfaces. What we really like to see here is that the reflections are not very high. The plot referenced to 100 ohms and shows that the magnitude of reflections is below 10 dB through really the entire spectrum, where we might have the pathway to 112 gig at 30 gigahertz. It stays below 10 dB and then some to the higher frequencies. So this meets the target, meets the expectation, and we're happy to see that kind of return loss performance. With that, I'd like to turn it over to Ralph Page to talk through the active testing that he's done with the platform.
Hey, thanks, Steve. A lot of good detail in there. Welcome, everybody. Please don't be jealous. That's one of my cleaner benches. In the background there, you can see the PCFF emulation platform, white Tachyon board, I think that's Tachyon, and a couple of riser cards. And in the foreground, you can see one of what we call our FAE demonstrator boards. That board, that green board, contains two Credo semiconductor bald eagle chips, two retimer chips, generating a total of 32 channels, in this case of PRBS 31 at 56 gigabits per second PAM4 data. And what we're doing with that board, you can see we donate some of those signals to other connectors that we manufacture. You'll see two rather nice brass-looking connectors there. The one on the right is our Bullseye 40 connect. And what we're doing is we're taking 4 channels of PRBS 31 data, 56 gig PAM4, and we're taking those 4 channels for those signals to one of the riser cards through about 14 inches of coax into some SMA connectors. There, we take 2 of those signals and we take them through our Gen-Z Scalable Connector through the backplane to a second riser card, where the signals then come back through another 14 inches of coax, back to our Bullseye and back to the retimer. The other 2 signals that went to the first riser card then travel through our Accelerate connector through about 14 inches of our twin-ax cable to the second riser card, where the signals go back. So we have 4 channels at PRBS 31, 56 gigabits per second PAM4 data running at the same time. And if we just switch now to the next screen, we'll see some of the test results that we got. We do? There we go. So what we can see there, the top 2 rows are the signals that actually go through about 14 inches of our twin-X high-speed cable. So those riser cards could clearly be at the extremities of that rack and then some. And you can see we have really good eye heights to the millivolts or thereabouts. In fact, the top one is 0 errors, and that's been running for about 24 hours. You can check that calculation if you like at 56 gig PAM4. You can see the total number of bits that we sent. And those are real generated eyes that we can measure at any time from the Credo Bald Eagle devices. Unfortunately, when we do an eye read, it's destructive, so we have to reset the counters again. So we don't do that in real time, we just do it as needed. And in fact, even the second channel of that has got a total bit error count of just 12. So it's managing e to the 15 or e to the minus 15 bit error rate. And remember, those bit errors are, there's no FEC, there's no error correction, no forward error correction in that. The second two rows are, and again, the top one of those has 0 errors. Those are the signals that go through the backplane and through our Gen-Z Scalable Connector. So again, very good performance. Now this is at 56 gigabits per second PAM4. We've also successfully demonstrated this emulation chassis at 32 gigatransfers per second also. And later this year, we'll be able to demonstrate it at 112 gigabits per second PAM4. That's about it, I think, for me. So I think, is it back to you, Matt?
Thanks, Ralph. Yeah, we appreciate that detail. So just want to have a brief summary before we jump into the Q&A. A couple of the key points would ask the audience to take away. Samtec has shown, as well as the Gen-Z Consortium has shown, that the Gen-Z Scalable Connector defined by SFF TA 1002 offers a pathway to 112 gigabit transfer per second performance with PAM4. We talked earlier also about how and showed how PECFF provides benefits and optimizes data center resources via disaggregation and the flexibility and scalability of the Gen-Z fabric. And the key point, being a member of the Gen-Z Consortium ecosystem, Samtec's PECFF emulation platform provides an easy-to-use solution with validated data for those that are interested in designing PECFF infrastructure. We do have the PECFF emulation platform available for customer use. If that's something that you're interested in, or if you'd like to request a demo in person, maybe virtual with the environment that we're in. But we can provide more information to our customers. Please feel free to contact Samtec at kitsandboards at samtec.com. And then for all information regarding Gen-Z, please log on to the genzconsortium.org website. Rachel, I think we'll turn back over to you for the Q&A portion of the webinar.
Great, thanks, Matt. Okay. We have a few questions today, actually. So first, I'm going to start with a question that says, PCIe Gen 6 is targeting 64 GTs of PAM4 signaling, but with lighter FEC implementation as compared with 802.3 FEC. Can PECFF 4C connector support this signaling? It's a big mouthful of questions.
So this is Steve. I'll take the question. The short answer is yes. The Gen-Z chose the scalable connector form factor specifically that was capable of 64 gig PAM4 all the way up to 112 gig PAM4 with that in mind. So the answer is yes, and then some.
Great, thanks. The next question that we have is, isn't the PECFF card wider than the standard PCIe cards? It says this is an advance, right?
I'll take that question. The whole advantage or benefit of PECFF is that it does leverage the mechanical infrastructure of the PCIe CEM AICs. So PECFF and PCI Express are mechanically compatible. Whether there is additional width within that, I would have to take that question offline to provide more detail.
Great, thanks. The next question is Top Edge connector similar in functionality to SLI connector in NVIDIA graphics cards?
This is Matt. I'll take that one. From a functional standpoint in general, yes. In both applications, the idea of top edge connectivity is to provide additional signal density, additional bandwidth, additional throughput between AICs. So whether you're looking at PECFF or the NVIDIA graphics infrastructure, that functionality at the system level is very, very similar.
Great. And then there was a question that came up, I believe, in the last few slides that you were presenting that stated, so what happens when you go to PAM to the losses? Was that tested?
So this is Ralph. I could answer that. So yeah, we'd obviously tested it with PAM4, as you could see there. One thing to note when I was showing you those where we got a couple of errors on 2 of the 4 channels, none of the channels were optimized in any way. I simply hooked up the Credo Bald Eagle chips and let it auto-adapt for a few hundred milliseconds and then let it fly. No doubt with some tuning of preempters or whatever on the transmit or even on the receive, we could probably get that to be even lower than it already is, very low. Steve, do you have anything else you could add to that?
No, that's fair. Yeah,
Okay.
You've effectively really tested and demonstrated the PAM4 capability that was really thought about beforehand by Gen-Z, and you're just proving it out. Yep.
So we're not quite 6 there. We're not quite Gen 6. We're not quite 64, but we are at 56. It's pretty close.
Okay, we have a few more questions here. One has just come in while you were speaking, so I'm going to go ahead and go with that question right now. It says, so you need retimers from Credo, I think is what they're asking, or can you not use retimers?
Sure, you can use retimers from Credo. They make very good retimers. No, you don't need retimers. We're simply using retimers as instead of bit error generators and scopes and VNAs and all that kind of good stuff to give a more real world test, if you like, of how this thing can perform. The retimers are cool because they have the bit error Gbps generators in them. We can adjust the clock frequencies. We can go NRZ, PAM4, and they're capable of even displaying an eye, which is so. We're not using them for their intended use, but they come in very handy for us.
Great. So another question that came through was, has Samtec tried testing the PECFF emulation platform at higher data rates like 112 gigabytes per second PAM4? If so, what results have you achieved?
So this is Ralph. I can answer that one again. So I have tried it, but only a single channel because that's the only hardware I had available. So that was 112 PAM4. That was also with a Credo chip, test chip actually, and I think we were achieving E to the 12, E to the 13 was what we were achieving in the time that I had it. But I will stress that it was only a single channel. We're going to have 4 channels available. I would say in another 8 to 12 weeks, we'll actually have 4 channels. This time a test chip from another company is going to provide a longer reach test chip. So we'll be able to try that. And we'll publish that data.
Okay, another question. In the webinar, you mentioned the insertion loss and return loss of the Gen-Z Scalable Connector. What about crosstalk?
Oh, sure. I'll take that one. The crosstalk for the Gen-Z Scalable Connector certainly has a pathway all the way up to 112 gig PAM4. So it's certainly capable. We didn't include it because there are quite a few different ways to represent crosstalk, and that maybe didn't fit in the hour of our webinar here to go into far end power sums, near end power sums, different ways to look at it. But yes, it's capable. Thank you.
Okay, and looks like I'm going to do one last question because we've gotten this question. I know you touched on it during the presentation, but we've gotten this question multiple times in a lot of different formats. So the question is, when will a PECFF motherboard be available? What company is making the PECFF motherboard? And are there any motherboards out there yet with PECFF connectors? So it's all kind of one tied up question, I think, but if you guys could provide an answer there, that'd be great.
Yeah, I'll take that one. And I think that's a fair question from a lot of the audience members. I'll start with the easy question, or the easy answer is that the PECFF emulation platform is already available from Samtec. So anyone that's interested in, using the platform that we've developed to test the infrastructure from an SI perspective, we're more than happy to collaborate with them and figure out the best way to support those needs going forward. And as we mentioned, companies interested in doing that can contact us at kitsandboards@samtec.com. In terms of other commercially available ATX motherboards with PECFF, I personally am unaware of solutions available. That's not to say that they're not there, but I personally have not seen them yet. I think that based on some of the chatter we've seen on this webinar, as well as some of the questions that Samtec has entertained from various customers in the recent history, I would say that the industry is moving towards that, but when and how, obviously, still TBD.
Great, thank you, Matt. Thanks so much. That's all the questions that we have right now.
All right, we want to thank everybody for standing in for our presentation. Thanks to Steve and thanks to Ralph for their technical assistance in the presentation. If any of the listeners have any questions for Steve, Ralph, or I, please feel free to contact us at our email addresses shown here. And please follow the Gen-Z Consortium social media for the latest information on all things from Gen-Z. Thanks again, everybody, and we'll look forward to seeing you on the next Gen-Z webinar in a few weeks.
Thank you so much, Matt. Thanks, Matt, Steve, and Ralph. We appreciate you so much for presenting today on behalf of Samtec and Gen-Z Consortium. We do want to remind everyone that the next Gen-Z webinar in our technical series will take place on Tuesday, September 15th at 11 o'clock a.m. Pacific time and 2 o'clock p.m. Eastern time. The title of that webinar is Platform Software Development Kits for Gen-Z Enablement, and presenters from IntelliProp, Smart, Bitware, and HPE will be presenting during that webinar. Again, please do follow us on social media at Gen-Z Consortium and contact us with any questions you may have. Thank you for joining.